So we talked about glyceraldehyde having that chiral carbon. If you take a look over here, you can see that this is the only chiral carbon in this molecule. This is not chiral and this is not chiral. And if you remember in organic, we said that there's free rotation about the carbon-carbon single bond, and it doesn't matter if it's this way or this way, it's all the same molecule. But then we introduced the term geometric isomers. Remember we talked about cis-trans isomers because something was rigid and whatever is up, whatever is down is down. All right, so I'm going to expand on that concept of geometric isomers and encompass this big term called stereoisomers. Stereoisomers are molecules that are isomers, but they are geometrically a little different. And in biochemistry, we have a type of stereoisomer called an enantiomer. I'm going to write that word down. Enantiomer. Enantiomers are mirror images of each other. And what I mean by mirror image is that at the chiral carbon, whatever is pointing in one direction, whether it's left or right, in one molecule, it's pointing in the exact opposite direction in the other molecule. Those are considered enantiomers. We're not focusing on the non-chiral carbons, just the chiral carbons. So let's take a look at these two glyceraldehydes. You recognize that this is glyceraldehyde, an aldotriose, and we said already that this was the only chiral carbon. Now take a look at this chiral carbon. See the OH group? See how it's pointing to the right here? And the only difference between this molecule and this molecule is that at this chiral carbon, the OH is pointing to the left. So these are called enantiomers. If it's pointing to the right, the OH at the chiral carbon, the one that is furthest away from the aldehyde group. So this is the chiral carbon furthest away from the aldehyde group. It's pointing to the right. We call it D for dextro. So D, this is D glyceraldehyde. Glyceraldehyde. And then this one, the OH group on the chiral carbon, furthest away from, forgot the aldehyde group. Furthest away from the aldehyde group, it's pointing to the left. So we put L for levo, and then this is L glyceraldehyde. So enantiomers are mirror images of each other. They're a type of stereoisomer. All of the OHs on the chiral carbons are flipped. Okay? You'll see this as we progress on with all the other monosaccharides. All right? So I'm going to skip over the tetroses, the 4-carbon monosaccharides. You can look them over in your book. I'm going to move on to the pentoses. There are 2 pentoses I'd like to talk to you guys about because we're going to be seeing them in DNA and RNA. So let's first do ribose, which is found in RNA, and let's draw the structure of ribose. It's 5 carbons. Okay, so 5 carbons is carbon 1, 2, 3, 4, 5. You can see that this is a chiral carbon. It has 4 totally different groups on it. This is a chiral carbon, 4 totally different groups. This is chiral also. This one is not chiral because there are 2 hydrogens here. All right. In order to determine if something is D or L, we look at the highest numbered chiral carbon, the one that's furthest away from the aldehyde group, the one that has the highest number. So if this is carbon 1, 2, 3, 4, so we're going to look at this one. This is not chiral, so we don't look at this. The OH is pointing to the right. Remember how we said right is D, dextrose? So this is going to be D ribose, okay? Now, if we wanted to do L-ribose, we flip all the chiral carbons. So whatever is to the right goes to the left, whatever is to the left goes to the right. Well, it looks like these are the only 3 chiral carbons, so these are the only 3 that are going to be flipped. So I'm going to draw out L-ribose over here. And the aldehyde group remains the same. Carbon 2, carbon 3, carbon 4. This one sometimes we just abbreviate as CH2OH because it really doesn't matter. It's not chiral, so it doesn't matter where everything is. But these, it matters. This goes to the left. This goes to the left. This goes to the left. And these guys are enantiomers. All right? Now, deoxyribose looks exactly like ribose, except carbon number 2 doesn't have an oxygen in it. So that's the big difference between the sugar in DNA and the sugar in RNA, is that the sugar in DNA, which is deoxyribose, has no oxygen here. So I'm going to just change the name here, and I'm going to draw out deoxyribose. I'm going to get rid of this O, so you can see that now carbon number 2 is not chiral because it's got 2 hydrogens on it. And over here, get rid of the O here also. Okay, so this is D-deoxyribose, this is L-deoxyribose. All right, and we're going to be seeing these when we're drawing the structure of DNA and RNA. Okay, again, which ones are the chiral carbons? In deoxyribose, it would be carbon 3 and carbon 4. What determines D versus L? The direction of the OH in the highest number chiral carbon, meaning the carbon that is furthest away from that aldehyde functional group. Okay? All right, moving on to the hexoses. These are now nutritionally important monosaccharides. We're going to be dealing with glucose and fructose and galactose. These are the nutritionally important ones. You've heard of glucose. Glucose is blood sugar. Fructose is fruit sugar. And galactose is just a component, a part of milk sugar. Excuse me, there's a disaccharide called lactose that we're going to be talking about, and galactose is part of lactose. And lactose is the only carbohydrate in all your dairy products. Okay, let's first start off with glucose. Glucose is an aldohexose. It's got an aldehyde group, and it's got a total of 6 carbons. 1, 2, 3, 4, 5, 6. Okay, let's do this. All right, carbon number 1 is an aldehyde. Carbon number 2 is an OH group pointing to the right. Carbon number 3, OH group pointing to the left. Carbon 4 looks like this. Carbon 5 looks like this. And then carbon 6 is not chiral, so it doesn't really matter how you do it. If you take a look at this, you will see that this is chiral, this is chiral, this is chiral, this is chiral. So carbons 2, 3, 4, and 5 are chiral. What will determine if this is D or L glucose? The highest numbered chiral carbon. So it would be carbon number 5. You notice it's pointing to the right. Right is D, so this is D glucose. All right, now let's do its enantiomer. L-glucose. L-glucose is everything is flipped. So anything that is chiral, that is to the right, gets flipped over to the left. Okay? So here we go. This carbon 2, carbon 3, carbon 4, carbon 5. Why am I squishing it like this? Carbon 1, 2, 3, 4, 5, and 6. All right. So this was to the right, this becomes to the left. This was to the left, this goes to the right. This was to the right, this goes to the left. This was to the right, this goes to the left. And then this one does not matter because it is not chiral. Doesn't matter. My CH2OH does not matter at all. Okay, and I'm just filling in the hydrogens. These are all expanded open chain Fisher projections. That's what we're doing right now. Okay, you can see why this is L. It is a mirror image of the D. Everything's been flipped, but there is a specific reason it's L. You go to the highest numbered chiral carbon, which is carbon number 5. The OH is pointing to the left, and that's why this is L-glucose. Okay, so we have two more hexoses that we're going to be drawing. We have fructose, which is a ketohexose, and we have galactose, which is a aldohexose. Galactose and glucose have a special relationship, and we'll talk about that in the next video.